So yesterday we were studying this a end-to-end call procedure for attach and how the components are involved in communicating with each other and achieving the purpose of making the mobile equipment gets connected to the LTE network. We have studied it as a procedure. Of course, we need to look into this aspect from log analysis point of view also. So we need to do a lot of log analysis as well. So even before we go into the log analysis, we take up the step to the next immediate level. So the final level we will be going into is log level. So here what we do. We consider LTE components and we already knew which component is what. The mobile node B, you have the MMES gateway, P gateway, HSS. This is PCRF and then PDM. And you have your AR, Equipment Identity Register. MME connected to the databases and mobile to eNode B, eNode B to S gateway user link only. S gateway to P gateway user link and as well as control link. P gateway communicating with the PCRF for the purpose of PCC rules. So this is the coordinating components in LTE. Now, how do we have to summarize the whole LTE component operation? We are interested in that at the starting. So by just removing those pictures, I have placed it with some blank boxes. Now I'm going to fill these blank boxes with the details that are needed for our understanding. So at the starting, mobile starts with the RRC connection with the eNode B. So obviously, even before the RRC connection, mobile will have these details stored on his SIM card. IMSI number, MSISD, and K. These three things would be stored on his side. These are the IDs. K is for your authentication related purposes, ciphering related purposes. We use this K. And then we have the same details that are stored on your mobile side have also got stored on your HSS, IMSI, MSISD, and K got stored on your HSS, HSS plus authentication center component, and the HSS also would contain the subscription information of the user. These are the permanently stored information. Of course, on the mobile side, subscription information won't be stored directly. But on the HSS side, subscription information would get stored. Okay, so what next? We have, along with this, the other information that mobile would be storing, the network would be storing about the mobile is its IMEI number. So mobile will have its IMEI number, and your EAR knows whether the IMEI number that you are using is in whitelist, gray list, or blacklist. It would know the details. Okay. None of the procedures that happened between mobile and any network element. This is a static storage. The information we have here is a static storage, and this always would be there. It's a forever scenario. Okay. Now at this stage, what happens? Mobile indeed started triggering its procedures. So the first procedure mobile triggers is towards your eNode B, and once he starts communicating with the eNode B, once the communication is completed, eNode B accepts RRC connection procedure and allocates one ID called as CRNTI, Cell Radio Network Temporary Identifier. It would allocate to the mobile. So eNode B has got a CRNTI and mobile has got the CRNT allocated. Okay, great. Um, so additionally, one extra ID now got allocated for the mobile. Next, what happens? Mobile now starts sending the NAS protocol message towards MME to request for the attach. So it again starts communicating, and the message comes to eNode B. eNode B prepares a eNode B U S1 API ID, and it would be um, it would start sending the S1 AP message towards MME. So what details is going to keep in this S1 AP message, which is going to send to the MME? It is a S1 AP message containing the NAS message, which is attach request plus PDN connectivity request. But to recognize the mobile uniquely on this link, where thousands of users' information will be exchanged, for every user there should be a unique ID created. eNodeB creates one and MME creates one as per the LTE procedures. But because right now eNodeB is initiating, only eNodeB created it. But once this information is indeed communicated to MME would note down that eNodeB UES1 API ID for the purpose of dealing with that number in the future. It would note it down. So we have eNodeB UES1 API ID. Great. Then what does MME do? MME received this message, and MME got to understand mobile equipment IMSI number. After opening the NAS message received, it understood this IMSI number. So what does the MME do here after receiving the NAS message? MME decides to first validate whether the mobile is a genuine guy or not. It decides to validate. In order to validate whether the user is a genuine guy or not, MME definitely need to consult HSS for the help. So MME to HSS, the link we are going to have is a diameter link. So what does MME do? MME, by establishing a new session ID, because for every transaction that happens between two diameter components in even on LTE, we must have this session ID working. So by having a session ID created, MME starts communicating with the HSS. But what number will be sent by MME is this IMSI number. He will pack it into this message called as authentication information request and send the authentication information request message to HSS. HSS receives that session ID, but after receiving that session ID, it will store the session ID, but he starts preparing the information needed for the MME. What kind of details? With the help of K, and in this message, MME sends a parameter called as a parameter called as PLMN ID. Right now, mobile equipment is connecting to which PLMN, that information will be sent. By using this PLMN ID, your HSS plus authentication component can generate something called as authentication token, AUTN, and it can generate one random number. It'll have to start creating all the needed authentication parameters. So it generates random number and authentication token. From these two things, your HSS would be generating first CKIK. From CKIK, it will be deriving KASME, and it will also calculate a parameter called as XRES, which is the validation parameter needed for the MME to validate whether the mobile is genuine or not, XRES. So by packing these details, random number authentication token, XRES and KASME, these details, a reply would be sent back with the same session ID from HSS to MME. The reply would come back. So MME now gets to know XRES, KASME, the key, and the random number and authentication token. Why MME need these details? MME need this random number and authentication token to send it to the mobile. Uh, KSME to calculate the keys that are required for NAS purposes and etc. etc. XRES is the one that we are going to request from the mobile to send. Once mobile sends the XRES, we need to compare that XRES with this XRES. We needed to compare that. That's absolutely needed. Okay. So that's the XRES part. All right. Um, so, so what's going to happen next? This session ID that has got created for the user to like exchange the um, subscription information between MME and HSS need not be kept permanently, because we already learned in our previous classes that the session gets terminated implicitly without explicitly signaling it also. Once the transaction is complete, the session must be terminated. So the moment the session is terminating, HSS will be destroying all the parameters that it has created for this user, because he never need to store this information, but HSS won't destroy it. Session ID will be gone. The other parameters like say XRES, ASME, random number, authentication token are not needed to be stored in HSS. If HSS wants, he can generate those parameters once again. He's having that capability. So all that is gone. But here the most important point is MME learned the information needed. That is the most important part. So MME learned that. Okay, what next? We are having here. Um, so MME starts creating a MME UES1 API ID for the user and starts communicating it with the eNode B and sending a NAS message to the eNode B. The NAS message called as authentication request. Now MME will attach its own S1 API ID and code the eNode B that next time onwards when you are communicating to me related to this particular mobile, use this ID. With this ID only I can recognize the mobile. MME is sending this to eNode B, coupling with this eNode B S1 API ID. So once that ID is sent to eNode B learned it. Next time onwards, they would be using these two IDs for recognizing this user. What next would happen here? Um, so the NAS message that is prepared is authentication request. So the authentication request arrived at eNode B. What does eNode B do? Pack that NAS message and he takes the responsibility of sending it to the mobile equipment by packing it into RRC. So by using the radio mechanism, eNode B sends this NAS message to UE in a message called as downlink information transfer. Mobile receives it, and when mobile opens the NAS message, he gets random number and authentication token from it. So what does mobile do? By using this K random number and authentication token, mobile can calculate CKIK and as well as XRES. Mobile would keep the CKIK with itself, but he is supposed to send this XRES back to MME. So what does the mobile do? Mobile prepares a NAS message called as authentication response, and he starts sending that authentication response in a RRC message, and that comes to eNode B, and eNode B would be again sending it on this link with these IDs. It would be sent to MME. MME, once MME receives this XRES, it will validate whether that XRES is genuine or not genuine. How we can validate? Just MME need to compare this XRES with the XRES received from the HSS. because the parameters that are considered are same. K is the same if the parameters are same. XRES also must be same because algorithm that is present in HSS and as well as mobile is the same software algorithm. Output is also should be same. So MME does the comparison and conclude that mobile is a genuine guy. Then MME now decides, now it is the time for activating the security mechanism for the mobile. It decides that. So what is he going to do? Immediately, with the help of this KASME, MME calculates the needed keys. It calculates the NAS integrity key and NAS encryption key. It would be generating these keys. NAS integrity key, NAS encryption key. We would generate. Okay, so um, now it is the time to order the mobile to enable the NAS security mechanism. So by using the NAS mechanism link, we send the information again to the node B in S1AP protocol. node B will dispatch it to the mobile equipment on RRC. Mobile receives it, security mode command, and the mobile decides to calculate these keys on his own by using the CKIK, and from that mobile can calculate KASME on his own, and from that KASME mobile also can calculate integrity key and encryption key as well. So it generates the KNAS encryption, KNAS integrity keys. Once these keys are generated, mobile accepts the NAS security mechanism. So it reports back, and the message comes back to MME. MME understands that mobile has enabled the security mechanism. So then what does mobile do? Then MME again requests for IMEI number, and now mobile sends the IMEI number here. Once mobile sends the IMEI number that is requested by MME, this guy gets the IMEI. MME gets the IMEI, whatever is requested. What we are going to perform? We take this IMEI and talk to AR. Ask him whether the IMEI is genuine or not. So this guy verifies and replies back and says whether this IMEI is a genuine IMEI or not. Once that is also proved to be perfect, MME is almost ready to accept the attach procedure that is triggered by the mobile. So what does MME do? MME will again create a new session ID to communicate with the HSS and ask him for subscription. Ask him for subscription information. He's going to ask for subscription details. Created the session ID, communicated with HSS, asked for subscription information, packed the subscription details, sent back. Now MME got the subscription information. The session ID will be terminated. So session ID will be existing only for the duration of your transaction. That is the specialty of LTE diameter operations. And once we got the subscription info, MME is ready to accept the activation of default bearer, and accept the attach. But before accepting the attach, MME is supposed to complete, he should start speaking to S gateway, P gateway, and PCRF to activate a default bearer and ask also these components to start creating the needed tunnels for user plane. So we need all that. So what are we going to do here to achieve this mechanism? So if you remember this step, if you go back to the previous step, so far in the procedure that we have studied yesterday, we have completed studying up to here. RRC connection happened, setup complete, attach request plus PDN connectivity request. So MME received that message on S1 AP. He talked to HSS and gathered the authentication details, challenged the mobile by sending authentication request. Mobile sent the XRES back to MME. MME validated that, started security mode. Mobile happily accepted that, and MME has requested for the mobile's IMEI number with the identity request, and UE has sent back, and we have sent that IMEI number to AR, validated whether the mobile is in whitelist, grey list, or blacklist. Once that is also proved, MME is going and communicating with HSS and gathering the subscription information. So, till now, whatever we have studied in those boxes, till we have completed up to this much part in in the procedure point of view, from the procedures point of view. Now, what part we have to complete? Now, this part we need to complete. So, before accepting the attach, what does MME is supposed to do? MME is supposed to start communicating with S gateway, P gateway, PCRF, and start creating the needed things. It starts creating that. So that is the task we have at hand right now, to complete this. Okay. So first we need to complete it towards the S gateway, P gateway side. Then we have to do these parts. All right. So we resume this operation. Okay, so what does ME do? ME creates one S11 control plane TEID. It creates one ID. So what does MME do after creating this ID? Because you don't know what ID S gateway is going to create, MME simply by using tunnel ID 0, it starts communicating with S gateway. The moment we communicated with S gateway notes down MME's control plane TEID. For future purposes, S gateway need it. Reason is, next time onwards, anytime when S gateway is communicating with MME, S gateway must code this TEID in the GTPC header, the one that is created by MME. Of course, MME should be using the tunnel ID created by S gateway, but because the MME never spoke to S gateway related to this user earlier, so we are creating that. We are going to use tunnel ID 0 for the first time when we are talking to S gateway about any new user. That logic would be applicable. So once S gateway gets this create session request message, S gateway understands, okay, MME is ordering me to create needed control plane tunnels as well as user plane tunnels. So what does S gateway do? S gateway first creates one user plane tunnel for the purpose of receiving the traffic from P gateway, which is S gateway user plane S5 TEID towards P gateway to receive the traffic from P gateway, and he creates another control plane tunnel ID, S gateway control plane S5 TEID. It creates. So for both our S5 TEIDs, which are going to be used by P gateway to send signaling message, P gateway uses this control plane tunnel ID to send user data. P gateway is going to use this user plane tunnel ID. So these two tunnel IDs, we use it for two different purposes. But fine. Now S gateway starts communicating with the P gateway. So S gateway sends out a message to the P gateway on this link. So P gateway gets to know whatever the tunnel ID created by S gateway, it notes it down, and then P gateway also notes down the tunnel ID that is created by S gateway for the user plane purpose. It notes down the tunnel ID, but that stuff is not completed yet. Before P gateway responds back to S gateway by creating the remaining tunnels, first P gateway need to take the permission from PCRF, telling him that there is a default bearer getting activated and you have to ask him for the PCC rules. We have to do that. So what does what does this component would do? like our P gateway would do. Uh, P gateway to PCRF, the protocol we are using is diameter. For all diameter transactions, we need to use this session ID mechanism. So your P gateway creates a session ID and starts communicating with PCRF by providing the IMSI number, etc. It talks to PCRF, asks him for the PCC rules. So it gets the session ID, it gets that IMSI that is sent by the P gateway. Of course, P gateway got the IMSI number from S gateway. S gateway got it from MME. MME would include that IMSI number in the message. So your PCRF derives the PCC rules and he sends back that PCC rule information back to P gateway. So P gateway gets that PCC rule details, which what is the filtering criteria, what is the billing rule, and what is the quality of service associated with it, what is the QCI, etc., etc. Everything we will get to know. We got it. Okay. So what's the next step that you are going to do after receiving this? And again, session ID will not be permanent. Whatever that is created for the transaction between P gateway and your PCRF. So this session ID will be removed again. But our duty is completed, getting the PCC rules. Okay, because PCRF accepted for the bearer establishment for this user and provided these PCC rules happily as well. So P gateway decides to proceed further. The first thing P gateway does is allocate IP address to the mobile, UEIP address. Once the IP address has got allocated, so then what is he going to do once the IP address gets allocated? This way, you have to create the other tunnels also needed. So P gateway creates one user plane tunnel ID for the purpose of S gateway to give it to S gateway to make S gateway use it to send the uplink traffic. Already he got S gateway's tunnel ID to send the downlink traffic from his side to S gateway, but now you need to help S gateway to send the uplink traffic to him with this tunnel ID. Plus, he requires to create, of course, he'll have a TF traffic flow template and EPS bearer ID associated with it. Fine. Then it is going to have P gateway's control plane tunnel ID as well. It creates. This P gateway control plane tunnel ID is going to be useful for S gateway to communicate to P gateway from next time onwards related to this user. So that is the control plane tunnel ID. So by including all these details, P gateway starts replying back to S gateway. S gateway notes down all this information. Oh, this is the P gateway's control plane tunnel ID. Next time onwards, if I have to send any signaling message to P gateway, I have to use this tunnel ID in the header. He will note down. S gateway also notes down the tunnel ID created by the P gateway. S gateway says, okay, if I have to send any uplink traffic to the P gateway for this particular mobile's default bearer, I have to send it on this tunnel ID, which is created. Now, because we have created both S gateway set tunnel ID, P gateway set tunnel ID, we can happily say that S5 set bearer has got established. S5 set bearer is created right now. The default bearer, one link is got created so far. Still, S1 bearer is not yet finished. Radio bearer is not yet created, but S5 S8 has got created. Okay. Now, S gateway does the remaining task. S gateway is going to note down the EPS bearer ID associated with it, and then it will note down the user plane tunnel ID that it is going to be giving it to eNode B. The tunnel ID needed for the eNode B to send uplink traffic. It has created the tunnel ID. S gateway user plane S1 tunnel ID. Okay. So after creating this tunnel ID, S gateway will create one more tunnel ID. This is for receiving the traffic from eNode B. This is for receiving the traffic from P gateway. Two different tunnel IDs, one for uplink, one for downlink. Okay. Now S gateway will create one last one control tunnel ID. S gateway control S11 TEAD it creates. So after creating this TEAD, S gateway responds back to MME. Now MME will get a lot of details. S gateway's control plane TEAD. Next time onwards, if MME need to communicate to S gateway about this particular user, it must be quoting this tunnel ID in the header. Should not be using tunnel ID 0. Tunnel ID 0 is only one-time usage. So the S gateway's user plane tunnel ID that is arrived from the S gateway, P gateway's control plane tunnel ID, P gateway's user plane tunnel ID, everything, all that information is available for MME. And MME also will get to know mobile equipment's IP address information in this response. He has got that IP address details as well. Okay, so what does MME do now? So MME says, okay, because I have successfully completed all the needed creation on the network side, it is now my time to create the same things on the radio side as well, on eNode B and as well as your mobile equipment. So I have to do this also. That's what that is what your MME thinks. So MME prepares a message called as initial UE context setup message and sends it to eNode B by packing a NAS message called as attach accept plus default bearer activation request. By including those two details, we would be sending this message to eNode B. So eNode B, it will note down the EPS bearer ID, of course. And of course, yeah, one important thing, MME will create one GUTI for the mobile, stands for Global Unique Temporary Identifier. Because MME is accepting the mobile's attach procedure, so definitely MME need to allocate this GUTI. Instead of using IMSI every time, next time onwards, mobile may use this GUTI to communicate with the MME. A temporary ID, but which is unique because MME will include his ID details also into it. Country code, network code, MME group ID, MME ID, then followed by whatever the ID that is allocated by MME, the MTMC number. It will be including all those details there. And then the reply would come back. So K node B will be attached by MME. It will derive the K node B from the this KASME information he has got, just like how he has derived NAS integrity key, NAS encryption key. It is also going to generate K node B now. So by attaching all these details, we send initial UE context setup request with the NAS message present inside it to eNode B. So eNode B gets this. He notes down the K eNode B because that is present as part of S1AP message, and of course eNode B gets to know what is the tunnel ID that is created by S gateway for sending uplink traffic to S gateway. He got to know that information, and also from this K eNode B, your eNode B can compute user plane encryption key, RRC encryption key, RRC integrity key. So what does eNode B do? eNode B decides to first activate the security mode, because the condition in LTE is that before you enable the before you create any data radio bearer or SRB2, you must enable the PDCP level security. So we have calculated the keys that are needed from this K eNode B provided by MME. So eNode B requires this K eNode B. He cannot generate the keys on his own because he doesn't have any K available with him. He never stores it. K is available only in mobile and HSS. Only these are the two components who can help generating the primary needed things to generate the keys. So, but ultimately, once K eNode B available, this guy can derive the keys. So eNode B triggers the security mode command. and mobile replies back with security mode complete. And of course, mobile also will calculate these three keys: user plane encryption key, RRC encryption key, RRC integrity key from these CKIK that he has calculated from this random number and authentication and token and K. From that, he will be able to generate these keys as well from KSME. Once all this is ready, mobile accepts the security mode command. So it explains it to Inode B, I'm accepting your security mode command. So once the security mode is activated, now we send RRC connection reconfiguration request once again. So in this RRC connection reconfiguration request, Inode B asks the mobile, I'm asking you to create a data radio bearer, a DRB, as part of your default bearer. We needed a radio bearer. Please create that. So you know to be commanded UE to do that. And along with that, whatever the NAS message that is sent from MME, the NAS message will be packed into that RFC connection reconfiguration message. That message goes to UE. UE's RFC protocol receives the NAS message and forward it to NAS layer, and what is he going to do next after the NAS procedure? It would be after the NAS procedure, your after the NAS message is received, first he responds back with the RRC part. He sends RRC connection setup complete. The moment he sends RRC connection setup complete, we can consider that the DRB is successfully created on the radio interface. Corresponding RLC got created, MAC got created, logical channel configuration and physical channel configuration, etc. So we have created a for a radio bearer related to a EPS bearer ID with particular traffic flow template. So this is done. Now, now ENODB decides to respond back to MME that about this success. It will be reporting initial UE context setup response. Of course, mobile's NAS layer receives this NAS message and note down what is the GUTI allocated to it and what is the IP address allocated to it. IP address is allocated by P gateway. It arrived from P gateway to S gateway to MME. MME packed that IP address in a NAS message and sent that NAS message to the mobile along with this GUTI. So mobile got the GUTI and as well as IP address. He noted down. Now, meanwhile, ENODB have created the radio bearer ID and created the linking, and now ENODB creates ENODB's tunnel ID to give it to the S gateway. ENODB user plane S1 tunnel ID to receive the traffic from the S gateway. You need to provide this tunnel ID details to S gateway, but ENODB can never provide the tunnel ID directly to S gateway because there is no control interface available. So ENODB packs this ENODB user plane tunnel ID in a message called as initial UE context setup response, and he sends it back to MME. So once MME receives this ENODB user plane S1 TEID, he receives one extra tunnel ID, and MME is ready to provide this tunnel ID details to who? It ready to provide it to your S gateway. But before that, mobile need to accept his activation of the default bearer. So now mobile prepares the next NAS message and send it. Once the NAS message arrives, we start communicating this information to S gateway. So S gateway gets ENODB user plane S1 TEID, and from now onwards here we can send downlink traffic also to the ENODB. For S gateway can send downlink traffic, ENODB can send uplink traffic to S gateway. So we can consider even this link is also got created between ENODB to your S gateway. So by achieving the overall communication procedure by using all protocols we have studied so far, RRC, S1AP, diameter, GTPC, and diameter again between P gateway to PCRF. Here it is diameter. This is GTPC, this is GTPC, this is S1AP, this is RRC. Mobile to MME, it is NAS. By using all these things, and here it is diameter, what we have achieved ultimately is decided to create and successfully created the needed, your EPS bearer, which is nothing but a DRB plus yeah, data radio bearer on the radio bearer plus S1 bearer plus S5 S8 bearer between P gateway to S gateway. Of course, your external bearer would always would be present between P gateway to the PDN in the form of an IP routing service with the help of IP routers, so that you don't need to create separately, but we consider that as existing. Now, just imagine in your head, this is the kind of information each component will store when one mobile equipment comes into the connected state. So what do you have to imagine in your brain is, what if another mobile comes into the picture? If the mobile is coming into the connected state, same package of information will be there. And now eNodeB will contain another set of these parameters, one more set it will contain, because for the new user we need to have new sets of information. This whole package of information, another one more package will be present on MME. Same thing is applicable for S gateway, P gateway as well. So all these components are creating same number of parameters every time a new mobile equipment gets connected. Now, not only two mobiles would get connected to the LTE network. That is wrong. It can be n number of users that will be connected to the LTE network. So for every user, each node has got a lot of information to maintain as long as the mobile equipment is in registered state and connected state. All these components would be maintaining these details to recognize that mobile equipment's signaling related needs, and to recognize that mobile equipment's user plane related needs, user data transfer related needs, to exchange everything. So that's the primary point we have there. All right. So what is next for us? So if we go back to the previous slide, so now the communication happened like this. Create session happened. Initially we context security mode command and complete RRC reconfiguration to create the radio bearer, default radio bearer, data radio bearer, and then be responding back to MME. Once MME gets the permission from the mobile to activate the default bearer, then MME sends modify bearer request to S gateway, and S gateway sends back, accepts it. Then finally, of course, one message that goes from MME to HSS is notify request and notify answer, that is sent. All right. So we are done with that thing. By taking that into consideration, we guys are now going to study the log analysis part. Okay. So let us look into this log file. So log files actually can be in different formats. Log file can be either in a Wireshark format, or some log files can also be there in text format also. Right now we are studying a log that is collected on a MME which is taking up this text format, which is present in the text format. So later we will study Wireshark logs also, but we are studying the data in the text format right now. So in on the MME side, we are able to, if we study this log that is collected on MME, we can only see diameter messages, we can see GTPC messages, we can see S1AP messages. If DNS is used for some purposes, DNS is also used. Why is that? I will explain. We will be able to see DNS messages, NAS messages. If MME is communicating with MSC, we can see SGS messages. And if MME is communicating with SGSNs by using old GTPC protocol, like version 1 GTPC protocol, we can use version 1 GTPC. So difference between that and eGTPC is eGTPC is version 2 here in this case, which represents LTE GTPC. So if MME communicates with S gateway, MME communicates with MME, we can always use GTP version 2. But if MME is communicating with S gateway, if S gateway supports version 2, we are willing to use version 2 itself. But if SGSN is not the old component, SGSN is not willing to communicate with version 2, it doesn't support version 2, for example, then we must be using version 1 GTPC. But this highlighted part here will tell us that in this LTE log file, what and all the information we would be able to see. That is what is got highlighted here. Fine. So we'll not be able to see all the messages. So you have to be careful about the thinking here. Even though we are going to study a attached log file, but we will not be able to see RRC protocol messages, for example. We cannot see X2AP messages. Another example, we cannot see the GTPC messages that are going on between S gateway to P gateway. We cannot see that. Like this, multiple different details we cannot see. I will be able to explain the things later only. So yeah. Okay. So what now? So okay. We have got our first diameter message that is outgoing from the MME. Outbound represents going out, the diameter message. So this IP address is going to be your MME's IP address, and this is the port number on which MME is operating, and this is the IP address of the receiving diameter component. It could be DRA or it could be HSS, and it is going to receive the traffic on this port number 3868. So MME's IP address is different, and DRA component's IP address is different. And we already knew that every diameter message contains these many fields in the header, followed by the AVPs, one or more AVPs. So in the message header part, we have version field present. Version value is set to 1. Message length is 92, represents 92 bytes of message. This is whichever the tool that is that has captured this log and displaying the information here is actually displaying the information not in binary. It is displaying the parameter values in two formats. One is in hexadecimal format, it is displaying, and this in the bracket, it is showing the same thing in the decimal format. So this 0x notation is always hexadecimal. Whenever you have two hexadecimal characters, typically that will be equal to 1 byte of data. If you remember our diameter protocol, version field is exactly 1 byte, and our message length field is 3 bytes, 24 bits. So we can see that there are 6 hexadecimal characters here. Each hexadecimal character is equal to 4 bits. So 6 into 4, 24 bits it is going to be. So this is hexadecimal representation. The corresponding decimal value is 92. Why it is displaying the information in two different number systems? Whoever designed this tool, which captured the data on MME, the people who designed it thought that it will be better for the human beings if it is present in programming mechanism. In most of the programming, we use hexadecimal notations, so we have to display it in hexadecimal, and decimal will be easily readable for the humans. We display it in decimal as well. So they have decided to display it in two different formats. So if you take this decimal value 92, corresponding hexadecimal value is 5C only, but all the leading zeros, leading characters are going to be set to zeros on the left, leftmost part. Basically, the most significant part will be filled with zeros. So four dummy zeros, and then we have 5C. Indeed, actually speaking, this will be converted into 32-bit of binary information when we are sending it on the actual wire. Because on the wire, we can never be able to send hexadecimal or decimal or octal directly. We cannot send. What we can send on the wire is binary. But when we have to convert it into the binary, we definitely need to convert it into 32 bits. So how do we convert it into 32 bits? What is the logic here to convert it? These are only 8 bits. So this 5C value corresponds to just 8 bits. But remaining all the bits will be set to zeros. How many zeros? 4 hexadecimal zeros. 4 hexadecimal zeros corresponds to totally 16 binary zeros, because every hexadecimal zero, when it is converted into binary, it is equivalent to 4 zeros. If hexadecimal value is 1, when it is converted into binary, it will be 0001. If it is a 2, it's got converted into 0010. It's like that. So if we have here 5C, 5 value is 0101. If you take it, that is what is got highlighted here. This part 0101 is 5. C is 1110. Uh, so maximum value we have is F to F, which is 1111, the maximum value for the hexadecimal number. So that is the hexadecimal to binary conversion. So if these 4 zeros, these are hexadecimal zeros, will be replaced with 16 binary zeros. These are 16. This 5C gets converted into 8 bits on its own merit. So 16 plus 8, totally it is 24-bit information when we are sending it on the wire. So on the wire, it is always in bit format. But why it is not showing the information in the bit format? The tool developers thought that bit format is useless for human beings. Human beings are not good in reading bits. Very difficult for us. So to read the binary information, so they're not displaying it. That doesn't mean that the information is in hexadecimal or decimal. No, actual information is in binary format, but it is displaying only in hexadecimal and decimal format. Okay. Command flags. What is the value? Hexadecimal value is 80 for the command flags. So if you take hexadecimal value 80, converted into decimal, it is equal to 128. If you convert this 128 into binary, we have 100,040. What this value typically represent? These 8 bits are 8 flags. If you remember our diameter protocol from our previous study, we know that in the diameter protocol header, your command flags are exactly 8 bits, and they would be these command flags are 8 bits. So first bit is R, P, E, T, R, 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 R. Whichever bits are set to 1, those are set to 1. So this bit is set to 1 right now. Remaining all the bits are set to zeros, because the value that we are sending is 128. When you convert it into binary, only the first bit is set to 1. Remaining all the bits set to zeros. So that is why what do we see here is 100,000 and 4 zeros. This value 80 or the 128 represents that binary information. Depending on the binary, we can see that request flag is set. Remaining none of the flags are set. it is displaying. Wireshark is, sorry, your tool is displaying that information. Next, command code is 280, that is reserved for device watchdog request on our diameter interfaces. This command code 280. So it's a general message. Device watchdog request command code is 280, and application ID is 0, represents it is a diameter common message. It is not a 6A message, because this is a common message indeed. And then we have hop by hop ID followed by end-to-end ID. Hop by hop ID is one number, end-to-end ID is some other number, which are used for their own purposes. The numbers can be anything decided by the component. So MME is deciding hop by hop ID to be this, or end-to-end ID to be this for their own purposes. These are 32-bit values. Even application ID is also 32-bit value. 8 hexadecimal characters, 8 into 4, 32 bits. So this is 1 byte, this is 3 bytes. 1 byte, 3 bytes. There itself is 8 bytes. Another 4 bytes, 12, 12 plus 4, 16, 16 plus 4, 20 bytes is your header. Standard diameter header is 20 bytes. Followed by that, we have AVPs. What AVPs we have in device watchdog request? Origin host, AVP containing its own parameters. This origin host thing is containing what are that things that are containing origin host part code. First AVP code, then followed by its own flags and AVP length. Vendor ID will be present or not will be dependent on this V flag. So first one is AVP code. What is AVP code? 264. 264 code is representing origin host. How do you know that? That is from the specification itself. So if you look in here, origin host, the command code is 264. The command code is okay. And for origin host, what are the AVPs? So what are the AVP flag values must be set to in for origin host field? Mandatory flag is must. We must set the mandatory flag to 1. If you want, you can set the P flag. Protected flag, you may set it to 1, but you must never set V flag to 1. Vendor ID flag to 1. Vendor ID flag must not be set to 1. That means only allowed flags that are allowed to be set to 1 is mandatory flag and protected flag. V flag is not set to. That means origin host never belongs to any proprietary node. Origin host AVP is defined by IETF or IANA, and it is applicable for everybody. It is not doesn't belong to any particular organization to keep a vendor ID. Not required. So that is why vendor ID flag will never be set to 1. Only M and P would be set to 1. So if you, by following that rule, if you look into these details here, in this AVP flags, value is 40 value. Value 40, when we convert hexadecimal value 40 into decimal, it represents a 64. If you convert 64 into binary, the flags weight that we get is 01000000. Now if you look at it, this is the vendor ID flag, this 0. This 1 is mandatory flag, and this next 0 is protected flag, whether we want the protection or not. So this is vendor ID. So vendor ID is set to 0, mandatory is set to 1, protected may be set to 1, but we did not set it to 1. We set it to 0, and remaining all the flags are zeros there because they are reserved anyway. The remaining flags. So that's what it is displaying here. It is telling us that this is the mandatory information 64. So as a protocol tester, as a protocol log analyzer, you must be comfortable in converting hexadecimal decimal into binary, binary back into hexadecimal and decimal or octal. So you must be really good with the number systems. You have to, if it takes time, you have to take some time and practice how to do the conversions from decimal to hexadecimal to binary to back to the other things. So you better practice it to understand that number systems better. Okay, fine. Length is 39 bytes we have, and your data that is present here is how much is the data size? Is 31 characters. So 31 bytes is the data size, which is the text. Um, 31 bytes plus header is 8 bytes. How do we know that the header is 8 bytes only? It's pretty simple. If you take the AVPs, if you take the AVP, uh, if vendor ID is not present, you have the header only 8 bytes. This is 4 bytes. All these flags is 1 byte. AVP length is 3 bytes. Together 4 plus 1 plus 3 is totally 8 bytes of header. So if the data is 31 bytes, 31 plus 8 is 39. So this AVP length will contain a value 39. It represents a value 39. Explains what is where we have to cut the first AVP on the received data size. It represents that. So that is what it is, 39. And this is the name of the MME. MME is quoting that my name is 0001 hyphen dam proxy.mme1.starn.com. So this part is the name of the MME, and this is the domain name, starn.com, which is REM, we call it as. So REM could be like this, or REM could be containing mobile network code, mobile country code, and the 3GPP network details, etc. It can be designed in that way also. The designing of it is obviously dependent on IANA. It is on the basis of IANA. But because this log file is collected on a test network, they have used a simple simple naming mechanism instead of using a complex 3GPP thing. Of course, you are allowed to use even the complex 3GPP thing also. And second AVP is origin REM. Code is 296 for origin REM. Flags, again, only mandatory flag is set. Length is 19 bytes. So again, 8 bytes is the header. 19 minus 8, the data should be 11 bytes. As you can see here, 11 characters. Each character is converted into 1 byte, 11 bytes of information. Origin state ID is the third parameter, which is the restart counter value. And again, the code is 278 for this. And the flags is 040. Again, mandatory flag is only set to 1. And the length is 12 bytes. That means this is not, this is basically a number. This number should be converted into 4 bytes value. This is not characters. This is not English characters. If it is English characters, ASCII characters, alphanumeric characters, each character we have to convert it into 1 byte of information. But when we have a number always can be converted into binary value. Each character need not be converted into binary separately. So we can take the entire number one time by pasting the value here, and we can convert it into binary. So this is the converted binary information. It is 4 bytes of information that would be there for us. So this is 4 bytes plus 12 is header is 8 bytes, is totally 12 bytes. Okay, so total what is the size? Your header is 20 bytes fixed. 20 plus 39 is 59 plus 19. 59 plus 19, 78 plus 12, 90 bytes. The total size should be 90 bytes. But why it is mentioned here as 92 bytes? There is a reason for that. What is the reason? In LT, for LT operations, for LT operations, especially not only in LT but in diameter overall, if there is a rule that AVPs must be 4 byte aligned. So what is the meaning of 4-byte aligned? The entire AVP size should be 4-byte aligned. 39 is not 4-byte aligned. 4-byte aligned means if you take the total length and divide it with 4, the remainder should be 0. Then only we consider it as 4-byte aligned. If this is 40 bytes, it would have been 40 bytes divided with 40. Remainder is going to be 0. But because it is 39, 39 divided by 4, we get a remainder 3. That means we need to add 1 byte of padding to make it 40 byte and to make it 4-byte aligned. So that padding part won't be displayed here, but definitely one byte of padding is attached here to make the AVP AVP becomes 40 bytes, even though the actual information is only 39 bytes. In the length, we'll mention it as 39 bytes. We just add some dummy 1 byte of information, of course, which will be thrown away into the dustbin by the receiver. Same way, here also we have 19. 19 divided by 4. Again, we have the remainder 3. We have to attach 1 byte of padding to make it 20 without having any remainder. So we need to add 1 byte of padding here, obviously. So 1 byte padding here. So 12 divided by 4, you will not have any remainder left out. We don't need to add any padding for this guy. So we have added 1 byte of padding for this, 1 byte of padding for this. These 2 bytes together, it has become 92. But the actual data, other than the padding part that is getting attached, is only 90. 90 plus 2 bytes of padding needed for these two AVPs. Only the AVPs which are not aligned, 4-byte aligned, those AVPs needed to be appended with this padding information. Other AVPs are not required. So that's the rule. Of course, the overall size is always going to be 4-byte aligned. 92 divided by 4, we will not have any remainder left. Okay. So what is we have sent a diameter outbound message, device watchdog request to DRA. What DRA will respond back? DRA will inbound with you are getting a reply back in the reverse direction 51.1 to 51.40. These are the reverse IP addresses. We are receiving it back. Device watchdog answer. Now, when we are receiving device watchdog answer, command flag is 0. That means even request flag is not set to 1. Earlier, only request flag was set to 1. If you remember the header, earlier only request flag was set to 1 when the value was 128. But now the value is 0. Even request flag is not set to 1, represents answer. But for device watchdog request and device watchdog answer, code is going to be same, 280 only. Code is same. But depending on the flag, request flag, we know whether it is request or answer. We would be able to separate those two things out. So then we have the hop by hop ID, end-to-end ID, the same hop by hop ID, end-to-end ID, but the message length is 104. If the message length is incremented means, because header cannot be incremented, header is of fixed size 20 bytes, we can easily imagine that there are extra AVPs present in this response message, device watchdog answer. So what AVPs we have? First AVP is result code. Result code is containing mandatory parameter. For result code, the AVP number is 268 and length of it is 12 bytes and the data is containing a value 2001. This 2001 is a code in diameter to represent a diameter success. That means whoever is responding back with the device watchdog answer, that component is telling you that hey man, whatever the diameter procedure you have initiated, I'm reporting a success for that with the diameter response. So a diameter success, that is result code. Of course, this is extra 12 bytes and the other guy who is responding back is sending origin host, which is 40 bytes of information, origin rem, which is torrent.com, which is 19 bytes of information, and origin state ID is a reset number of restarts happened, that number that is again under 12 bytes. Only padding we need to add is this for this guy, because this guy is already 40 bytes. The amount of data is already 4 byte aligned. We don't need to attach any padding for this guy. So this guy don't need any padding, this guy don't need any padding, this guy don't need any padding. Only this guy need 1 byte of padding. So by adding that 1 byte, so plus these extra 12 bytes that we are adding for the result code, so total size has become 104. 92 plus extra 12 has become 104. So earlier diameter message also is containing the same AVPs. These three AVPs are similar in the earlier case also. This is now the extra AVP that is coming up, the result code AVP. All right. So why the MME and the DRA components are exchanging? Why these components are exchanging your what do we call it? Um, these diameter messages like device watcher request. When there is no active diameter messages going on in order to validate whether the component is dead or alive, you would be using this device watchdog mechanism. So this is some kind of a way of finding out if the other component is dead or alive. So that's why these components are exchanging this device watchdog request and device watchdog answer. Next, inbound. We have device watchdog request received one more time. This is inbound. This time it is coming from the DRA. DRA is sending his own device watchdog request. So because it is coming inbound with 96 bytes of information by adding details, so you are going to send back device watchdog answer outbound. You would be sending it back. So these messages will continue till the actual active diameter messages are going on. But anyway, we have result code, origin host, origin remind, origin state ID part present. Okay. So what is the actual message that is starting right now here? There is an inbound message arriving from eNode B on S1AP interface. This is the eNode B's IP address, eNode B's port number. This is MME's IP address, MME's port number on S1 interface. Every interface, MME can have a different IP address. MME has got a different IP address for diameter. MME is having a different IP address for receiving the traffic from eNode B for S1 interface. And the S1 message that we are receiving is the initializing message. It is not a successful answer or a failure. It is an initializing message. S1 setup. It is S1 setup request we are receiving. And in this S1 setup request, we have 4 IEs, information elements present. In diameter, we would be calling the parameters as AVPs, but in all other 3GPP based protocols, we would be calling parameters as IEs, information elements. So the first information element that we have is eNode B global ID. So eNode B, which is proposing the S1 setup procedure, it is conveying its own global ID, and it is conveying that the PLM and ID that I belong to is 214365, and my eNode B ID is this 0007P. Together, none of the eNode Bs in the world will contain the same ID. If you combine this PLM and ID plus this eNode B ID, no two eNode Bs will have the same ID. Either the PLM and ID will change. If the PLM and ID is the same in one operator's PLMN, every eNode B must be having a different ID. Operators will have to make sure that they configure a different ID for every eNode B. So that is the combination. We call it as a global unique eNode B ID. This is eNode B global unique ID. Okay. So that is the most important thing. I have ignored some of the parts here. Like I have already explained you what is the meaning of criticality. Reject criticality means if this IE cannot be understood by the receiver, receiver must reject this procedure, must send a failure to this procedure. That is the meaning of it. Reject criticality. This extension bit will explain whether the data, whether IE will have some extension information or not. So the IE extensions are not present. That means it will be finished at standard size that is known to S1AP protocol. it will finish that there. Okay, what next? We have second IE we have right now, IE2 we having. So what is IE2? So IE2 is inode B name we have. So some name which is present in the form of a text. So the 60 recognizes that this is inode B name. So for every IE, there will be one ID. With the help of the ID, sender and receiver can identify what kind of IE it is. So 65, 6E, 62, 31. Okay, great. That is inode B name. Then we have supported tracking areas. What are the supported tracking areas? The tracking area supported by inode B on his cells. So number of items he is sending. This is the third IE. This third IE is containing two items. Item 1 is explaining what is the first tracking area code. Tracking area code 92A belongs to PLM and ID 214365. And second tracking area code 934, and that also belongs to same PLM and ID. That means totally inode B is having two tracking areas. And of course, inode B is not explaining MME how many cells it is containing. It can be 3 cells, it can be 6 cells, it can be 12 cells, it can be 24 cells, depending on the inode B's complexity. But irrespective of the number of cells that are present in an inode B, but inode B is having those cells grouped into two tracking areas, 92A and 934. If this tracking area information is useful for MME to perform something called as paging mechanism. If any incoming calls arrive for the mobile, so you have to distribute the paging messages. We use this tracking areas. So MME must know which tracking areas are available under which inode base, so that MME can happily distribute the paging messages without having any problems. So this whole thing is the third IE. And please remember, this PLM and ID is written in, uh, something called as a Little Indian format. So when the data is displayed in the Little Indian format, you have to you have to read it like this. If you remove the hexadecimal, you have to read it this way. So basically, you have to read it from right to left on every line, every 1 byte of information. So the actual value is 1, 2, 3, 4, 5, 6, whenever it is written in the Little Indian format. So that represents 1, 2, 3, 4, 5, 6. So 1 to 3 is your mobile country code, and 4, 5, 6 is mobile network code. Your data that is present can be represented in Little Indian and Big Indian formats. What are those? I will explain later in the data coding techniques. But this is represented in Little Indian method. So, but when we are reading it, you have to understand it. So, even though you see, code as 2143 365, like that. So you should not be understanding it as the code as it is 365. If you see it, you'll have to actually understand it as 1, 2, 3, 4, 5, 6. So 1, 2, 3 is your mobile. 1, 2, 3 is your mobile network, mobile country code. 4, 5, 6 is mobile network code. That is how you have to read it. But anyhow, we see that again, but just telling you for that reason. Okay. Next, fourth IE that is present here, IE4, is default paging DRX. Value is set to version 32. So inode B is conveying MME. I would like to receive paging messages from you every 32 seconds once. I don't want to receive the paging messages continuously. That's inode B's proposal. Of course, MME accepts it, and MME sticks to that request. And then followed by this, we have an reply that is sent by the MME outbound S1 AP message. For this S1 setup procedure, successful outcome with reverse IP addresses and port numbers. So this is the MME's IP address. This is the inode B's IP address. and we are reporting successful outcome, and is containing three information elements. Of course, user IDs are not there in these messages because these are general messages. These are not UE specific messages. And we see MME name, that is a MME name we have, followed, that is one information element. And then the next information element is served GeoMMEIs representing MME is supporting how many groups. It is part of how many gummies. So how many gummy IDs it is having. So item one, you have PLM ID 214365 and group IDs, served group IDs. We have MME group ID and then MME code. That is that. So if you combine these three things, mobile country code, mobile network code, and MME group ID, and MME ID, finally, if you combine these four details, we call this as GUMI, Global Unique Mobility Management Identity. No two MMEs in the world will have the same ID. Either country code would be different, network code would be different, or group ID will be different. If the group ID is also same, ID will be different. Every MME will have a different ID, even though those MMEs belongs to same group, belongs to same network, belongs to same country, but ID will be different. At least one of the things will be different. Okay. The third IE is relative MME capacity set to value 255, which is the maximum value, representing that the MME capacity representation is 255, is going to be considered as 100%. If next time onwards, if load situation need to be reported by MME, if we report something like a value like 128, meaning is 128 is half of the value of 255, we understand it as MME is right now operating at a load of 50%. So it is like that. So this is a relative MME capacity index value 255. If E node B, even if E node B cannot understand it, you can ignore it because ignore is set as the criticality for this IE. But whereas this IE, second IE, served GeoMME IE, this is set to reject. Meaning is if this IE cannot be understood by E node B must reject the procedure. That is that. Okay. So S1 setup has happened. Next, inbound message is arriving. We are going to see S1 AP message, initial UE message. Initial UE message arrives from eNode B to MME after RRC connection is completed. Actually, it arrives after RRC connection is completed. So if you go and look into our procedure, first RRC connection request happens, RRC connection setup, RRC connection setup complete. In this, whatever NAS message is present, that would be packed into initial UE message, and on S1 AP message, we pack that NAS message and send it to MME. Now we are directly seeing this message. What happened to these three steps? RRC connection request setup and setup complete. Because these are taking place between UE and eNode B, we will not be able to see this RRC information in a log file that is collected on MME. Because in a log file that is collected on MME, we can only see the components which are interacting with MME or MME interacting with those components. But UE to eNode B communication can't be captured on MME. That is none of the business for MME. MME have no idea. So, but when we are receiving this, so we ourselves have to imagine in our head that this is already done. Wherever the UE is, wherever the eNode B is, they must have performed this procedure. Only after receiving the NAS message, eNode B is packing and sending. We are directly seeing this message because these things is not present in our log file as this information is available between UE and eNode B. Where do we study these log files then? We study this separately. UE log files one separate time. We would look into. Right now we are studying MME log. Um, so okay, so we have initial UE message. which is containing a NAS message, obviously. But how many IEs are present inside this initial UI message are 6. What are the information elements that S1AP message is packing? First one, enode BU S1 API ID. Now from now onwards, it is UI specific messages. For every UI specific message, we must create a initial enode BU S1 API ID. So we have 1, 2, 3, 4, 6 as the value of that for this enode BU ID. And then we have the NAS video. The actual purpose of sending this S1AP message itself is sending this NAS video. That is the actual purpose for us. So it is containing this NAS video. And what details are present in this NAS video? This big hexadecimal string is our NAS video. But if you decode this NAS message, what information you can see is you can see one EMM message. We can see one ESM message as well. We see two things, EMM and ESM. That is obviously true. If you look into this NAS message, EMM we have attach request, ESM we have PDN connectivity request. We have two things that are present there. So if you look into the EPS mobility management, the message type is attach request, and we are doing a EPS attach, and right now the mobile is not having any keys available. Key set identifier value is set to 7. Mobile identity is IMSI number. This is the IMSI number of the mobile. Every IMSI number will contain mobile country code plus mobile network code. Mobile country code is 123. Mobile network code is 456. This is the mobile subscriber identification number, MSIN. Together we call it as IMSI. 3 details together. That is the mobile's number, and UE network capability information we are packing and sending it to MME. It is going to be understood by MME, this network capability details. And then that is ESM message. But this EMM message, along with that we have a ESM message as well. ESM container, EPS session management message. So what is the session management message we have? So the message we are having here is PDN connectivity request, packet data network connectivity request, and it is an initial request, and the mobile is willing to connect to a PDN type IPv4 PDN, and there are some protocol configuration options, and we have decided to ignore that for time being. We have to study that as part of our advanced LTE sessions, these protocol config options. So we ignore for time being. Now next, mobile station network capability. We have what are the capability information we are sending. Mobile is quoting that I don't have any TMC available for me at this time, and mobile is reporting its preference, settings, voice domain preference and UE setting. Mobile is reporting to MME that on my Android phone configuration or iPhone configuration, the user has set as voice centric CSC is preferred and IMSPS calls are secondary. This is my present configuration that I can accept. Human being has configured my device for this configuration. Okay, so this is one IE. So the entire NAS message is packed into your S1AP message as a information element. So this is only one information element, but along with that S1AP is also containing 5 more information elements. Which are those 5 more information elements? We already have studied one thing, which is the enode S1AP UEID. Remaining 4 more information elements we have. What is this? The next information element is tracking area ID. What is the tracking area ID? Already, we reported the tracking area IDs with the 2 MME. Why it is sending the tracking area ID once again? After it has sent the tracking area details more already. This is not the entire tracking area list that EnodeB is processing. EnodeB is conveying to EnodeB is conveying to MME about mobile equipment present tracking area ID. So it is reporting that this mobile is right now present under this PLMN and under this tracking area code. If you remember, EnodeB reported that I have 2 tracking areas earlier in the setup procedure, but right now it is sending only 1 tracking area ID, which is 92A. That is where the mobile equipment is present under. and mobile equipment is made RRC connection under by being present in this tracking area. And then we have um, the Ultra cell ID. The next fourth IE is Ultra cell ID. So PLMN ID followed by the cell ID. Every cell ID will be extended with your eNode B ID. Up to this it is eNode B ID. This 00 is your cell ID, and eNode B ID would be same for every cell, and your cell ID will be changing. So if eNode B is having 3 cells, so eNode B ID would be same. Cell ID will be 000102. If eNode B is having 6 cells, it may become 03, 04, 05 like that. So the cell IDs will be extending. So this cell ID is 00, which is an extended version of eNode B ID itself. So cell IDs are also unique in the world. UTRAS CGI ID, cell global identity. This ID is globally unique. No two cells will have the same ID in the world. Okay, what is the cause? Mobile has quoted at the time of establishing RRC connection. Mobile has quoted that I'm performing MO signaling, mobile originated signaling procedure. So this is what mobile has quoted to eNode B. So eNode B is sending this information to MME. Hey man, I don't know what mobile is going to ask you, but at the time he is making a RRC connection, this is the reason quoted. If mobile is requesting for different services other than this, so you consider that mobile is not a genuine guy. But this is the reason he has quoted me when requesting for connection, RRC connection. Followed by if mobile is having any preference to connect to any MME, if these are default values, when these values are set to default value 8 all zeros, 8 all zeros, 8 all zeros, that means mobile equipment has not got any MME preference right now. Mobile is mobile is ready to be connected to any MME that be takes into. So that is the preference that mobile equipment has quoted as part of RRC procedure, and eNode B is conveying the same information to MME as part of this S1 AP message, S1 initial UE message. Okay. Now, this is the S1 AP message actually. In MME, what happens when MME receives the S1 AP message, MME separates the S1 AP parts and the NAS parts, and S1 AP protocol will read S1 AP parts, NAS part will be read by NAS protocol. That is why the separate NAS message will be shown once again. Every time we see the NAS messages 2 times. So the NAS message is nothing but it is a EPS mobility management message, EMM message, and it is attached request containing this IMSI number, and there is the ESM EPS session management, and these details PDN connectivity request, and so on and so forth. All these details are present. Same thing that we have seen earlier. Okay, so that is that. So what happens once we send the initial UE request? MME is supposed to go to talk to HSS, ask HSS for authentication details, and get back that authentication information. So MME starts preparing a diameter message this time. So MME is sending an outbound diameter message, which is authentication information request, which is code is 318, and it belongs to application ID 1677251, represents a 6A application which is sent from MME to HSS. Request flag is set to 1, proxy flag is set to 1 because the value is 192. 192 means if you convert into binary, first 2 bits will be set to 0. Once remaining all the bits will be set to zeros. So this value is 128. This value is 64. 128 plus 64 is 192. 32 is 0, 16 is 0, 8 is 0, 4 is 0, 2 is 0, 1 is 0. If all these things are also set to ones, the value will become 255 by adding up everything. But they are not. Okay. So this is a 6A information and this. So what details are being sent? So we are creating a session ID, one big session ID. It is some random string. It can be any big. It is ultimately MME's decision to decide what session ID you want to use. You can use a simple number or you can use a big string. It's obviously MME's choice. But the idea here is it must be unique for every user that is operating at the same time. Session ID will be unique. Authentication session state. Always in LTE, we will be using no state maintained. Origin host and origin rem. Origin host is MME ID. Origin rem is starn.com. And destination rem is included, is also starn.com. That means the user is trying to register with the MME that belongs to the same network. So MME belongs to the same network, HSS belongs to the same network. So both the places we have this starn.com present in both locations. We have this. Okay, so what do we do when we have this starn.com thing present here? So we have the user name here. User name is nothing but IP address, sorry, IMSI number. The IMSI number that is sent from mobile equipment to MME. MME is forwarding this username and asking for authentication details by including supported features. Supported features information is a grouped AVP containing AVPs inside AVP. Whenever you see these AVPs below this level, you have to understand them as they are present inside this AVP. Is called as a grouped AVP. Three AVPs are present inside this top AVP. So that is that. So supported features. MME is explaining his features. It is explaining that, hey, I belong to a vendor called as 10,415, meaning is 3GPP. I am sending you one feature list, and that is one, and the feature list itself. So in the form of feature list, it is sending a number. What happens to this number? If you take this number and convert it into binary, so if you take this number, paste it and convert into binary, it will be converted like this. What this represents? Each and every number represents one feature. 1 means that feature is enabled. 0 means the feature is disabled. So for it is 32-bit value. 32 bits will represent 32 features. So whichever bits are set to zeros, those features are disabled. Whichever bits are set to ones, those features are enabled. Remaining features are all disabled. So MME to HSS on the S6A, we can have around 32 features, and depending on which features on the MME side operator is enabling, we have to set those bits. MME would set those bits to ones and report it. That is the meaning of feature list. So once this is supported features is included, we will have additional information called as requested U-turn authentication information. Because it is the MME who is trying to authenticate the user, MME would like to send this U-turn authentication info, request for U-turn authentication info. How many vectors MME is requesting for? Number of vectors MME is requesting is 1. This is also grouped AVP. AVP is present inside AVP. So the number of requested vectors is 1. That means how many key sets MME is requesting? Only one key set. And ME is also requesting HSS that please try to provide this information immediately. I need it immediately right now. Right at this moment, I am making the mobile wait to authenticate him. If you can't provide it immediately, mobile will be delayed. So please prioritize this and send the reply immediately. That is the meaning of immediate response preferred. Okay, so what do we do once we have these details present? The requested U-turn authentication information, number of requested vectors, and the immediate response preferred. And also MME reporting what is the mobile equipment's visited PLMN ID. This PLMN ID is a very important factor while calculating the KASME. We require HSS need to calculate something called as KSME from random number and authentication token. So one of the parameter in this authentication token is this PLMN ID, mobiles present visiting PLMN ID. Along with the K, we we send all these things and generate CK, IK. From CK and IK, we would be generating KSME and send this KSME back to the MME. Of course, for the authentication purpose, yeah, your HSS need to calculate XRES also. Okay, so requesting node type is MME. Who is requesting it? MME is requesting it. Great. So what is going to be the reply? Inbound, that is the meaning of reply coming back. Authentication information answer. Only proxy flag is set to 1. Request flag is not set to 1 this time. That is why the value is displayed as 64. 64 corresponds to 0, 1 and all zeros, 6 zeros. First bit is 0, which is your request flag, and second bit is proxy flag. Only proxy flag is set to 1 and all zeros we have. So command code is the same, 318, and it is S6A, and we have hop by hop ID and end-to-end ID we have here, and the session ID and vendor specific application ID. We have vendor ID, authentication application ID 16777-251. So HSS is reporting that he is supporting this 3GPP technology vendor, and this application ID it is supporting, it is reporting back these details. And result code, what happened to the diameter procedure triggered by MME? It is a diameter success. And then we have authentication session state, no state maintained, meaning is it is not going to remember anything related to this user anymore. It will forget about this user. Origin host, origin rem represents HSS origin host ID, HSS domain. Domain is the same for MME and HSS because they both belong to same PLMN, but their IDs are different. And then supported features we have. So supported features next, AVP, vendor ID and feature list, number of feature lists, one feature list, and the feature list. Again, this information when it is decoded, it will get converted into 32 features. Those features are enabled, the remaining features are not. And the last but not least, the actual information we are requesting, that is authentication information. This AVP itself is a grouped AVP containing a lot of AVPs inside. Now, how many vectors HSS is sending back? Only one vector. If multiple vectors are sent, these kind of packages, multiple packages will be there. But this this time only one package is there. So this EUTRON vector is also a grouped AVP. Grouped AVP present inside another grouped AVP. Inside this EUTRON vector, what we have? We have 5 AVPs present inside this. One is item number. Item number is 2323. Some number, some ID for the authentication details that are sent. The random number that is generated by HSS. The XRES that is calculated by HSS. The authentication token, which is a combination of sequence number and PLMN ID details. By including it, we calculate this authentication token. So that authentication token, KASME, the key that is needed for calculating the rest of the keys at the MME side. So by attaching all these details, random number, XRES, authentication token, and KASME, by allocating one item ID to that, we would be sending one UTRA vector. If we have one more UTRA vector, for example, HSS can send 10 UTRA vectors also. MME will store almost all the UTRA vectors in his database. First time he will use only one UTRA vector. Next time when he need to authenticate the user one more time, it would be using the other vector. It would be using the other vector to it would be using the other vector to you use the other vector and validate the user. So MME can ask 10 vectors and store it and use those vectors one by one to validate the user in different times. He can do that. But this time he did not do it. He has requested exactly for one vector and we are sending exactly one list of things. If we have requested for one more, exactly the same thing will be present one more time. Item number maybe 2324, and you have one more random number corresponding the XRES, corresponding authentication token, corresponding KASME. All these things would be present. One more package would be present. Okay. So we'll stop here. So far we have studied these many steps. HSS replied back with authentication information answer to MMA. Remaining log we will study in our tomorrow's class.